first you'll be asked to prove whether you agreed to recording or not. And then we move ahead. Good morning, good afternoon, good evening, colleagues. So like I said before, this is day 2 of EUMETSAT's user preparation webinar on EPS-SG microwave sounding and imaging mission. So today we are going to the imaging mission. So our attempt is to cover all the microwave missions over these last 2 days. So MWS, MWI, and submillimeter imager, the ICI. I'm Srireka Thoniparambil. I manage the EPS-SG user preparation project at EUMETSAT. Together with my colleague, Stefan Buczynski, who is the MTG user preparation manager, we are organizing this series of next-gen user preparation webinar. The attempt is to cover all observation missions which are part of MTG and EPS-SG to give you information on all these missions. For those of you who were here yesterday, I hope you had a useful session. We had excellent talks on the MWS mission, and thanks also for your engagement during the Q&A and also for your feedback on the talks. And hence we move today to the imaging missions. We have the first 2 talks by Vinia Mattioli and Francisco De Angelis, who will give us an overview of MWI and ICI instrument, the calibration process, the product generation, formats, dissemination, etc. Although we know there's a long heritage for microwave images, both these imaging missions are new for EUMETSAT, and especially ICI is a particularly novel mission for the user community. So we have tried to include 2 more talks to touch upon the application perspective. So as is clear from the title of the talks by Susanne Krivel and Alan Gear, they are giving us they have aptly titled their talks, what new information are available from ICI, or how to prepare for an all-sky assimilation of MWI and ICI. Yes.
Sorry to interrupt a second. We do not see your screen as you're speaking now. And
I'm not sharing the screen.
Okay, if that's okay. Sorry for interruption.
No problem, Madeline. I'm just talking for myself. So that's it. So we have these 4 talks today. And again, before I just hand over to Vinia, who is giving the first talk, I will, like yesterday, I have 2 points on the logistics. One is to use Slido tool for asking you questions. There was a feedback yesterday, why do we not just use the Zoom chat? I mean, we just thought that in the Zoom chat there are a lot of messages coming, some information messages from us, some chats between the participants, so it's quite difficult to sift through all these messages. We thought that using Slido would help us to organize a bit better the Q&A, and we also would like to keep an archive of these questions in a better format. So Slido offers us such a facility. So anyway, so this is, you have to use the event code. You will be prompted to use a code. Type there NG-MW. You can also use your smartphone. You can also ask your questions anonymously if you prefer, or you can also put your name in there, and use the Zoom chat if you have any issues. We try our best. If you don't hear us very well, or any issues, just point into Zoom chat. And the second point is that we will make available all the presentation slides and Q&A session and the recording. There were a few questions yesterday whether we would make them available. Yes, we would make the material from this available to you. With that, I think I have covered all the points, and I hand over to Vinia. Vinia?
Hello, Srireka. Welcome everybody. I am Vinia Mattioli, and I'm responsible for the product development of the Ice Cloud Imager, and I also lead the microwave imaging team. And today I will present I will give an overview of the MWI and ICI missions.
Vinia, everything looks good. I'm going to mute. Yeah.
The EUMETSAT Polar System second generation, EPS-SG, represents the European component of the Joint Polar System, which was set up with NOAA to assure continuity of essential operational meteorological observations from polar orbit for numerical weather prediction, climate monitoring, atmospheric chemistry, and operational oceanography and hydrology. EPS-SG consists of two satellites, of two series of satellites in the same orbital plane, METOP-SGA and METOP-SGB, with 3 satellites for each series. And we span an operational lifetime of the program over 21 years. The orbit is the same as METOP, sun-synchronous, with 835 kilometer mean altitude, 9:30 of the local time of the descending node, and a repeat cycle of 29 days. The payload is complementary distributed between the two satellites. SETA is provided with infrared, microwave, and imaging instruments for sounding temperature, moisture, and trace gases in the atmosphere, with instruments such as ICI, 3MI, METIMAGE, Sentinel-5, and the microwave sounder MWS. SAT-B is provided with microwave instruments focused on microwave imaging of clouds and precipitation with the microwave imager MWI, the ice cloud imager ICI, and the scatterometer SCA that will provide observation of ocean surface wind and soil moisture. Both satellites include the radio occultation instrument. Why we need the MWI and ICI? Which are the mission objectives? The primary objective of ICI, of MWI, is to support the numerical weather prediction at regional and global scales through the provision of cloud and precipitation products, and to support nowcasting and very short range forecasting. Other objective is to support observations of the surface, including sea ice, snow parameters, and sea surface wind, and for this latter, to complement the scatterometer on the same platform. Finally, MWI will provide the continuity of key microwave imager channels in support of long-term climate records, and I will discuss this on the next slide. The primary objective of ICI is to support climate monitoring, the validation of ice cloud models, and the parameterization of ice clouds in weather and climate models through the provisions of ice cloud products, including bulk microphysical variables. Moreover, ICI will fill an operational gap, providing information on non-precipitating ice that is not covered either in the optical thermal infrared or in the millimeter wave range. And I will discuss this in a further slide. Key legacy microwave channels that for MWI are the 18.7, the 23.8, 31.4 and 89 have been exploited for a long time for the estimates of precipitation rate, total column water vapor and cloud liquid, as well as the surface parameters. Indeed, MWI has a direct heritage from instruments such as the US Department of Defense SSMI, which was launched back in 1987, and its successor, the SSMIS, as well as from NASA and JAXA missions, such as the Global Precipitation Mission TMI and GMI, as well as from the SMRI and SM2. Those instruments have provided a continuous long-term record of high-quality global satellite microwave observations in support of long-term climate records, which now extend over 30 years. In the upcoming time, together with the mission from JAXA, from CMA and Rosidromet, and EUMETSAT and ESA will contribute to the longer climate record from 2024-2025 onward with MWI, ICI, and with the Copernicus mission SIMR that will be devoted to surface operation observations. In the following slides, I will present MWI and ICI in detail, and I will discuss also the novelty of these two missions in terms of frequency channels, but also sampling and instantaneous field of view. ICI is the first operational radiometer of this type, specifically designed with the objective of responsive ice cloud. The use of submillimeter frequencies for the observation of cloud ice properties has been subject of several investigations. For instance, if we look at the image on the top left from Bauer et al. 2007, the enhanced sensitivity of measurements at different submillimeter frequencies to ice particle size is clearly shown as compared to the capability, for example, the 180 GHz in the light blue, or to the infrared and the radar capabilities in gray. The presentation of Suzanne later today will provide further insight on this. But I would like to say that ICI will open up the submillimeter region for NWP and climate monitoring. Measurements by other instruments at this wavelength already exist, although mainly from link sounding instruments, as for instance from the Aura MLS or Odin SMR, or from demonstrational CubeSat missions. Airborne instruments have also been built, and I would like to mention especially ISMAR, which is the International Submillimeter Airborne Radiometer, jointly funded by Met Office and ESA, which is an ICI demonstrator and carries the same channels as ICI, also including the 118 and the 874 gigahertz. Now, looking at the MWI and ICI channels over the microwave and the submillimeter spectrum, the sampling capabilities of the two missions combined can be really appreciated. In the lower part, the legacy channels at 18, 23.8, 31.4, and 89 gigahertz provide information on precipitation and snowfall, total column water vapor and cloud liquid, as well as surface parameters such as sea ice and wind and snow cover. The missions also include the oxygenous absorption near the 50-60 complex and the novel channels at 118 gigahertz, which is an innovative feature of NWI, which will enable the retrieval of information on weaker precipitation and snowfall. NWI channels at 183 gigahertz will provide information on water vapor profiles and precipitations. And beyond, the innovative ICI channels around the weak absorption line at 325 and 448 gigahertz that will provide information related to the total column cloud ice and ice particle size. Plus, ICI will have two Windows channels at 243 and 664 in both polarizations that will provide information on ice habits and orientation. Now in the table, we can look in detail to the MWI channel characteristics, including the bandwidth and the footprint requirements and the noise equivalent delta temperature, the N delta T, which is an important parameter telling you what level of instrument noise it is to expect in the data. The objective is to have an instrument with the values in the table or better. MWI has 18 channels. Oops. MWI 1 to 3 and MWI 8 are the legacy channels as previously discussed. MWI 4 to 7 are in the oxygen complex at 50-60 gigahertz. And all channels from 1 to 8 are in double polarization VAH, while the channels above are in single polarization. MWI 9 to 12 are the channels innovative at 118 gigahertz as discussed in the oxygen absorption, while the last 5 channels from MWI 14 to 18 are slicing the water vapor absorption at 183 gigahertz. Looking in detail at the ICI characteristics. ICI has 11 channels, 3 spectral channels, ICI 1 to 3, are in the 183 gigahertz and are common to MWI. And this is to support the synergic use of the two instruments. ICI has 3 channels in the 325 gigahertz, ICI 5 to 7, and 3 channels in the 448 gigahertz, ICI 8 to ICI 10. MWI, ICI 4 and ICI 11 are the Windows channels, measuring both V and H polarization at 243 and 664 gigahertz. Now, how MWI ICI look like? MWI is about 1.8 meter high and is composed on a rotating part and a fixed part. The rotating part will include the main reflector antenna, the feed assembly, the receivers, and the control and data processing unit, the CDPU, that acquires the measurement data and performs the thermal control of the rotating part. The fixed part contains the hot calibration target, the cold sky reflector antenna, and the instrument control unit, the ECU, which is responsible for the instrument control and interface with the platform. MWI has a tubular structure in the rotating part that minimizes the sound intrusions inside the instrument cavity. In addition, an annular shield is also present on top of the hot target to provide a double thermal protection. The antenna is composed by an offset paraboloid reflector with a feed cluster of 7 horns. The feed horn accommodation and how this will reflect in the instantaneous field of view I'll discuss in a later slide. A direct detection is foreseen at 23.8 and 31.4 and 89 gigahertz, while heterodyne detection is for the other frequencies. Also, MWI 1 to MWI 3 have internal noise diodes to support the calibration and the nonlinearity calculation. Also, RFI, there is an RFI mitigation filter in the MWI 1 channel at 18.7 gigahertz. ICI will be about 0.7 meter high and about 1.2 meter wide. ICI also will consist of a fixed part and a rotating part, and will also have a sun shield, a scan mechanism assembly, interfaces between the two parts. The rotating part includes the main reflector antenna, here, the feed assembly, the receivers, and the CDPU. If you consider that ICI will observe in this direction, the radiation will come from this direction, goes in the main reflector and directly into the feed horn and the front end. And then the signal is given in the back end here below. The fixed part contains the hot calibration target, the cold sky reflector, and the ECU. And while it rotates, the feeds will see the OBCT and the cold sky reflector for signal from for a short window. The feed cluster is made of 2 rows of 7 horns, 4 and 3 per row, and with the row of 3 for the water vapor sounding, and the row 4 for the window channels that are also implemented with the with 1 horn per polarization. So it will be the 664 and the 243 gigahertz. For all the channel, a heterodyne detection and double sideband is foreseen. To perform the calibration, MWI and ICI, while rotating, observe the cold cosmic background as a cold target, and the onboard hot calibration target as a reference in specific observation windows for each rotations. These values are smoothed over few scans, allowing to compute the hot and the cold counts and the hot and effective hot and cold radiances in the calibration equation, as we can see in the figure, allowing to compute the gain and the offset of the calibration and provide the antenna radiance. Finally, an antenna pattern correction is performed for the main reflector spillover, losses, cross polarization, and side lobe to compute the top of atmosphere radiances. The calibration algorithm also accounts for the moon contamination in the cold view and provides a flag for the sun glint. Looking in detail to the calibration equation, the nonlinear transfer function for the two instruments is expressed as a third-order polynomial of the actually measured Earth view counts, CS, with 4 terms that express the third-order polynomial, A0 to A3. Starting from the computation of the linear gain and linear offset from the cold, warm, and the radiance, corresponding radiances, the nonlinear term and the nonlinear term, the offset and nonlinear gain can also be computed by including 2 nonlinear parameters, A2 and A3, which can be computed from cold and hot measurements and from the nonlinear parameter alphas that are derived from non-ground parameterization. Linear and nonlinear parameters are computed for each scan and will be provided in the level 1B output, as will be presented by Francesco later. Specifically for MWI, channels MWI 1 to 3 up to 31.4 GHz implement noise diodes that are activated every other turn in the instrument. The noise diodes provide 2 additional calibration points while observing the cold space and the Earth target, which are exploited to explicitly calculate the nonlinearity term of the calibration curve. Those points can also be used for a 2-point backup calibration approach, for example, in the case of calibration anomalies in the cold or hot load. For example, the other reference with noise diode on and off can be used to support. Now, looking at the MWI and ICI scanning characteristic, the figure shows MWI that will be on top of ICI, with both instruments passive conically scanning, rotating at a rate of about 0.75 Hz, which is 45 rotation per minute, with every scan lasting about 1.33 seconds. The observations are acquired at ±65 degrees in azimuth in the 4 view, with an incident angle of 53 ±2 degrees, giving a SWOT width of about 1,700 kilometers. ICI will be conically scanning counterclockwise, while MWI will be conically scanning clockwise, as seen from zenith. And the 2 instruments are not synchronized. Now I'll show a small video that to present how the scanning of the 2 instruments is performed, MWI and then ICI. Now, looking at the MWI instantaneous field of view, the 7 horn antennas of the MWI are placed at different positions in the focal plane, leading to a configuration of the instantaneous footprints at surface level as given in the figure on the left. The MWI footprint is about 50 km for MWI 1 and 2, as the average of the 2 footprint axes at 3 dB. And about 30 kilometers for MWI 327 and 10 kilometers for the higher frequency channels. An high across-track sampling is applied, providing a substantial overlap of sample footprints. The sampling time is about 0.39 milliseconds, providing about 1,400 samples per scan. The oversampling factor is about 20 for MWI 1 and 2, about 10 for MWI 327, and about 3.5 for MWI 8 to MWI 18. I would like to point out that the requirements for the delta T are defined for the footprint size. Therefore, the noise on the individual oversampled samples will be higher. The relative positions of the 3 dB footprints of a complete scan is also shown here on the right. Along track in this direction, the footprint overlap requirement is 20%. Now, looking at the ICI instantaneous field of view, as I previously mentioned, the 7 Hz antennas of ICI are placed in 2 rows with slightly different offsets, bringing the instantaneous field of view as given in the figure, with surface incidence in basically 2 rows, so with surface incident angles varying between 51.5 to 53.8. With the window channels below and the water vapor channels above, and the 183 be on the top, in the middle on the top. The horn antennas are designed to provide the same angular resolution between the channels, and the ICI ground footprint will be on average about 16 kilometers, with a footprint being elliptical with an access ratio approximately 3 to 5. The relative positions of the 3 dB footprints of the complete scan is also shown on the right. Also for ICI, an high across-track sampling is applied with measurements sampled every 0.66 milliseconds, giving 782 samples per scan per channel, and providing an overlap of about 3/4 in the across-track dimension. Along track, a 40% overlap for all the channels is expected. To highlight the potential of having MWI and ICI measurements on the same platform, these figures show the breast temperature simulations of the Harlech and Ike in September 2008, as you would have seen by the MWI and ICI instruments. At the MWI channels 18.7, 31.4, the brightness temperature increase due to the emission of the raindrop, while also the surface features can also be clearly seen. At 23.48 gigahertz, the water vapor emission is notable, while at 89 gigahertz and 165, there is the decrease with rain rate due to scattering by the precipitating ice above. The figures also show the potential of the cloud slicing capability in the oxygen band at 50 gigahertz and at 118 gigahertz for the light precipitation and snowfall. Looking at ICI, as we compare the high frequency channels with respect to the 183, which is current one of the highest channels operationally available, the strong sensitivity to the cloud ice and the ice particle size can be clearly seen. For the 325 gigahertz and the 448, the different sensitivities also from far the line toward the center of the line can also be seen. Finally, I would like to point out the strong TB depressions produced by the ice scattering at 664 gigahertz. With the last slide, I would like to give credit to the MWI and ICI Science Advisory Group, the SAG, which is our main interface with the user community, and 2 members of the SAG will also provide a presentation later on, Susanne and Alan. The SAG is composed of scientific experts with the objective of providing a frame for the scientific support and advice to EUMETSAT and ESA during the development of the MWI and ICI missions. SAG also comments on all aspects related to the proposed product processing, the product format, archiving, dissemination, reprocessing, and the CalVal. The SAG highlights the research and the development necessary to achieve the mission objective and to provide a longer-term outlook of the potential evolution of the objectives. In this respect, the SAG has drafted the MWI and ICI science plan with a lot of information on the application of the instruments, and this the science plan is available for consultation at the EUMETSAT website. I would like to thank you, everybody, for your attention.
Thanks, Vinia. Nice presentation, and you will be happy to know that we have about 95 participants listening to you. So let's see how the questions, okay? So I'll bring up the Slido page, Vinia, just bear with me for a minute. I'm stopping your screen share, okay, Vinia?
Okay.
And we have the questions here. A minute, please. Okay, I think this is a confusion regarding the launch date, which you had in your slide for Q4 2024, but in the documents in the web page, we have Q1 2025. I think Vinia, do you want to say anything or?
Yes, we can say that formally is still Q4 2024, as mentioned today, and unfortunately, this date can also slightly change because of foreseen delays. Probably Q1 2025 is probably more realistic than the still formal date provided, and that's why maybe the confusion.
There might be an update based on,
yes,
yeah, I think, but theoretically it's Q1 2025, or yeah, let's say, yeah, it might be postponed to 2025. I think we can take the next question, Vinia.
Yes.
This is about, will each of the, shall I highlight it? Then you can see it better.
Yes.
Will each of, because then you will know which question I am asking.
Yes.
There are several coming up. Will each of the 7 MWI scan lines have same ending starting points? That is, will all MWI channels have the same number of pixels across the scan line in level 1 product?
Yes, the answer is yes.
Okay, then I archive that question. It's an S, yeah. The next question, will there be a combined?
There is a, maybe I saw something about the line, because of course there is a slightly offset among the, so you will have the same number of scans and the same number of pixels, but of course some channel will look a bit forward and some channel will look a bit backward because of the different view. That's I would like to be precise on.
Okay, maybe when we give the final answer in writing, maybe you can explain it, because I just kicked the tick mark and the question went off, and if I have to bring it back, I don't know what to do. So maybe we can give a detailed
Yes.
explanation when we give the answers, when we give the written answers back to the participants. Sorry about that. The next question is, will there be a combined ICI MWA product with collocated and convolved TBs?
Currently, for the day 1 and day 2 of this of the mission is not currently foreseen, but of course we know that this is of interest of the users, and we have to see what will be possible in the future, but for the moment is not foreseen. There is a study that EUMETSAT has done to and is available, and the report is available in the website, to for the development of an algorithm and code to provide collocated and convolved TBs on top of each other for both MWI and ICI. Okay. Also together. So this in principle is a study that has been already done.
Mm-hmm. Okay, then I go to the next questions. What is the status of MWA ICI instruments? Are the instruments, I think it meant completed, yeah. Are the instruments completed?
They are under development, yes. The engineering model has been available for both instruments, and the proto-flight model is being developed in this as we speak.
I think there's a great curiosity to see these instruments. Okay, I think we answered that. What is the available data sources? Did you understand that question? I mean, it's not very clear to me, but go ahead if you understood it.
I have difficulties.
What is the available data source?
It can be that I will, Francesco De Angeli speaking, it can be that I will reply to this question in the next presentation.
Possibly. What data is available through
which
media?
format? Or
okay.
I mean, it could be that this is the explanation.
Thanks, Francesco. So I don't tick that question because maybe that will come later, because but we can bring the other one up. Can you suggest a research or a paper using this data, maybe, so we can see a real project used it, so we can know some techniques in working on those data?
MWI and ICI will be launched in Q1 2025. So at the moment, there is no real data available. But we, as EUMETSAT, we are providing test data to the users, so the users can test the algorithms, their algorithms for using and applying MWI and ICI data for their product developments, for example. Also, there are a lot of studies going on at the moment, for example, and a lot of and some papers that have been already published working with the simulated test data. For example, there is one paper that is from Patrick Erickson et al. That describes 2020, that describes the development of the ice water path algorithm using the test data. Also, there is a lot of studies that has been done for this for the new frequencies as well, or with MWI and ICI, how to combine this data. Susanne will also talk about this more.
Yeah, I think there's a lot of research in how to use this data. So hopefully, I mean, not using the real data, but yeah, let's see. Thanks, Vinia. I think I will take that off, but I think Susan, I will talk about this a bit more anyway. my controls are sometimes. Are there any particular challenge for the 664 gigahertz?
Well, for sure, there are a lot of technology challenges when you go high in the frequencies. I don't know, from the fact that you have to put the front end very close to the horns because you have to avoid the losses for even the small space between the horns and the front end can create a lot of losses. And also there are other challenges, for example, measuring an antenna pattern above 180 gigahertz. This posed a lot of challenges to the instrument manufacturer, actually starting from the simulation and from the measurements. And also, for example, the receiver technologies, how to measure the spectral response function of these channels. Definitely ICI has been pioneering. There are other instruments that have been developed, but this is going toward the high frequency channel has been a challenge for in several points of view.
Okay, good, Vinia, thank you. What is the rationale for the NEDT requirement differences between MWI and MWS?
The requirement for MWS, maybe Jörg can also confirm, but the requirement for MWS are for the water vapor profiling and temperature profiling, while MWI and ICI, for especially MWI, is for precipitation, which has less stringent requirements than MWS in this respect.
Okay, thanks, Vinia. I have one more question if we have time to take. Yes, we have time. So, Vinia, interesting that you note that the 118.75 gigahertz is useful for light rainfall and snowfall. The F53C MWHS and Tropics 118 gigahertz show little evidence of light precipitation sensitivity. It's about light precipitation.
Yes, the introducing the 118 gigahertz was based on an information content studies, also to be used in conjunction with the 50 gigahertz channels. So we will see once the data are in orbit how this compare to the other missions and if they can provide additional information.
Okay, I don't see any more question coming up except this one, which I keep just, in case we forget, but we are anyway talking about that. Let it remain there. But otherwise, Vinia, I think we are in time for a short break. Thank you for the presentation. Very good. And everyone, we are taking a small break of 5 minutes and we meet after 5 minutes. So that's a 5-minute break. I'm just telling it in CEST at 14:50. I think that is 12:50 UTC. Take a break. Hi, welcome back, everyone. I hope you had enough time for a break. Francesco, you may want to start now.
Yes. Good afternoon, everyone. I will share my screen. Just a second.
So we have Francisco De Angelis.
Yes, I'm going to present myself in a second.
Yes, please do.
So let's put the presentation mode. I will switch my screen. Yes, perfect. Now you should be able to see.
It's not your first slide, actually.
Yes, sorry. Yes, now it is.
Yes.
Okay.
You have to do it again, yeah.
Yes, perfect.
Good.
Okay, so good afternoon to everyone. I'm Francesco De Angelis. I'm the EUMETSAT remote sensing scientist dealing with the preparatory activities for the Microwave Imager MWI mission. Welcome to this presentation, which is focused on MWI and ICI level 1 and level 2 product formats, test data, and data dissemination. So these are the outlines of the presentation, which essentially follow the title of the presentation itself. I will introduce you the MWI and ICI level 1 and level 2 product. I will talk about the format and the test data that we have generated and we have released. And at the end, I will give you the overview of the EUMETSAT data dissemination baseline. So this is the overview of the MWI and ICI product centrally generated at the EUMETSAT headquarters. The level 1B product are the top of the atmosphere spectral radiances observed, of course, by ICI and MWI, geolocated, calibrated, and quality controlled. The level 2 product are the cloud liquid water path from the MWI data, and from ICI data, we have the cloud ice water path, the mean ice particle size by mass, and the mean mass I. The native format for both the level 1B and the level 2 product is the NetCDF4 format, following the climate and forecast metadata convention. The size of the file is 1,101 megabyte per orbit for MWI level 1B, 430 megabyte for ICI level 1B, and 85 megabyte for level 2. The name of the file reported in each first line of the two blocks, level 1B and level 2, gives to the users some useful information, like, for example, the generation time of the file and the start-end time of the product itself. It is worth to mention here at this point that in addition to the centrally generated product, we have also several level 2 and level 3 products that will be developed by the EUMETSAT satellite application facilities. So, for example, hydrology SAF, no-casting SAF, climate monitoring SAF, and OSI SAF. Okay, the EPS second generation system, including also MWI and ICI missions, supports three different kinds of mission. The global mission for the product generation and distribution of information acquired by the onboard instruments over the full globe, with an expected timeliness of 70 minutes for level 1B and 80 minutes for level 2 product. The regional mission for product generation and distribution of information over a specific region of interest, essentially over Europe and the North Atlantic area, as you can see from the picture that I reported here, with improved timeliness, such as 30 minutes for level 1B and 40 minutes for level 2 product. Finally, we have also the local mission that is only for our level 1B data for MWI and ICI. That is for the distribution of instrument data to user station via direct broadcast at any location with visibility of the satellites. Okay, now we move to talk about the format of the product files. This format is fully specified in the product formats specification documents. In the first line of this slide, I reported the link of the level 1B ICI and MWI product format specification. The structure of the NetCDF is common to all the EPS-SG missions and is described in details in the EPS-SG general product format specification, the GPFS. Also, the link of the GPFS is reported in the slide. This structure in terms of NetCDF group is reported also in the figure. The group that differs among the missions is the data group. Now I'm going to give you some more details on this group and its subgroups. So we start to talking about the navigation data group that provides information on the geolocation of the level 1B data. In particular, it contains the UTC start time of the Earth view for each scan. So not for all the sample, but only the first one of the scan. Then we provide the geolocation data, of course, but these geolocation data are not provided in full resolution, but are provided only in tie points over the ellipsoid. And they are provided not for all the channel, but only for Horn for ICI and data group for MWI. In the next slide, I will show you how the channels are grouped into Horn for ICI and data group for MWI. In this respect, I refer to latitude, longitude, observation zenith and azimuth angle, and solar zenith and azimuth angle. Then inside the navigation data group, we have also the orthorectified delta latitude and delta longitude, in this case in full resolution, in meters, not in degrees, that are needed to reconstruct the geolocation over the digital elevation model. We provide also the terrain elevation and the land fraction associated to each pixel. We provide some useful information like the sun glint angle flag, the moon angle, the RFI flag, so the radio frequency interference flag only for MWI1. And finally, is also included some additional information on the satellite navigation that is provided per scan, like the sub-satellite position and the spacecraft altitude and so on, some additional information. Okay, essentially the PFS contains some useful information on how to interpret the navigation data. For example, in the table that is also included in the PFS, there is the way the MWI and ICI channels are packed into data groups and Horn. In the PFS is also reported the procedure to reconstruct the geolocation data from tie points to full resolution. Essentially, it is a simple linear interpolation in time performed in the HF coordinates. It is also reported the reconstruction of the time for each Earth sample. And finally, we provide also the reconstruction of the orthorectified latitude and longitude over them using the delta latitude and delta longitude, and with the formulas that I reported here in the slide. Essentially, we have the geolocation on the ellipsoid, and then we provide this additional information to retrieve the geolocation over the dam for each in full resolution. Okay, going ahead with the description of the level 1B file, the measurement data contains the measurement data group contains the calibrated radiances in milliwatt on square meter, steradians, and centimeter to the -1. This time per channel, so for each channel, and in full resolution. In order to save space in the file, the data are not stored as a float, but as an integer. But the user can simply unpack this data using scale factor and offset contained in the attribute of each variables. Okay, Then we talk about the calibration data that have been already introduced by Vinia in the previous presentation. It contains useful information about the calibration processing, like, for example, the side lobe correction contribution that has been applied during the antenna calibration, the value of the calibration counts and their averages for both the cold and the hot load, the linear and nonlinear calibration coefficients. So I'm talking about gain, offset, nonlinear gain, nonlinear offset, and the A1, the A2, A3 coefficient that Vinia has mentioned in the previous slide. We provide also the noise diode status flag per scan for channel MWI1 to MWI3. And last but not least, we provide also in the file the value of the temperature detected by the temperature sensor mounted on the main components of the instruments that have been used for the radiometric correction during the calibration procedure. The quality information, processing flags, and quality groups provides overall indicator on the quality of the product and of the processing itself. For example, the calibration and navigation flags provide information on the calibration and the navigation procedures respectively. We have also some processing flags, we have gaps information, and the duration of data missing, degraded, and present in the file. Okay, now we move to talk about the level 2 output file. The structure you can simply recognize is the same of the level 1B file. I report also here the link to the PFS, the level 2 PFS, so product format specification for the description of the format. Here I'm going to talk about the two subgroups of the data group that are the liquid water path data and the ice water path data. The first, the liquid water path data, containing variable retrieved from the processing of the MWI data, and the second from the ICI data. Both the groups contains the UTC start time of each scan, the latitude and the longitude of each level 2 pixel that are different from the level 1 pixel, the surface type associated to each pixel. In the liquid water path data, we have the liquid water path, we have the total column water vapor that is included as a diagnostic variable, and of course we have also the corresponding retrieval error. In the ice water path data group, we have the ice water path, the mean particle diameter, and the mean ice mass height, as retrieved from the ICI data. And of course, we provide also the uncertainties in terms of cumulative distribution function. As additional field, the file provide also this group, provide also the latitude and the longitude associated to the mean ice mass height. Okay, now we move to talk about the first version of the test data that we have published at the EUMETSAT website. We reported the link in the yellow in this slide. This test data I will call it TDPV1 from now on. Okay, the TDPV1 has been published mainly for user familiarization with product format. It is based on a quarter of orbit over Africa, Atlantic Ocean, and North Antarctica. I will show you this slide in the this quarter of orbit in the next slides. This quarter of orbit contains 1,140 scans in a single granule. It is important to highlight here that this is not in line with the operational baseline because it foresees a 3 minutes processing window. So we are talking about 135 scans granules. The TDPV1 envisages only the nominal scenario. So not gaps, erroneous calibration counts, satellite maneuver, and so on, that will be considered instead in the second version that will come up in 2023. Some functionalities have not been implemented for TDPV1, like, for example, the side lobe correction, the boom correction, and the RFI processing for MWI1 on the level 1B processing. In the level 2 processing, we did not consider the computation of latitude and longitude of mean ice mass height from ICI data and the total column water vapor retrieval error from the MWI data. Okay, here I report the maps of the radiances from the TDPV1 for some of the MWI and ICI channels and the associated polarization. This is the considered quarter of orbit. We can see how this quarter of orbit contains most of the surface condition. We move from land over Africa. We have some open water here in the Atlantic Ocean, and we can see here at the bottom of the orbit, we have also a bit of sea ice. Also, the atmospheric conditions are well represented with some clear sky over Africa, some convection that will be more visible at higher frequency channel, and also some stratocumulus clouds. From left to right in this slide, I show you the lower frequency channel of MWI, so the 18 gigahertz, the 23 gigahertz, the 31 gigahertz, and at the end, the 50 gigahertz, all at V polarization. Be reminded that for this channel, we have available also the H polarization. Okay, now we move to talk about the higher MWI frequency channel from 89 to left. From left to right, we have 89 gigahertz, 118 gigahertz, 165 gigahertz, and finally 183 gigahertz. So here we can see how we are moving from the emission to the scattering regime, as Vinia has already mentioned in her presentation, in one of the last slides of her presentation. Here we can also see that how we increase the frequency, the signal from the surface disappears, and the signal from the atmosphere becomes the dominant one. Now I move to talk about the lower ICI frequency from 183 up to 325 with the 243 at double polarization, V and H. Here is again, I want to stress again that the 183 gigahertz is in common between MWI and ICI. And they are, of course, on the same platform. So this will allow to intercompare these channels between the two instruments. To conclude the overview of the level 1B radiances from TDPV1, I show you the higher ICI frequency channel, up to 664 gigahertz at V and H polarization. We can see how the ice clouds looks larger because the higher frequency channel are sensible to ice particles of smaller dimensions. Okay, this is now we move to the level 2 test data packet V1. Before talking about the test data packet V1 for the level 2, I want to introduce you the functional decomposition of the MWI and ICI level 2 processor. I show you this slide because I want to highlight that our level 2 processor is articulated into two parallel algorithms. A 1D-var approach, which retrieves the living water path from the MWI radiances and from a priori NWP forecast field by minimizing a cost function. Instead, a Bayesian Monte Carlo integration algorithm is used to derive the ICI level 2 product by exploiting a priori database of possible atmospheric states. Okay, here I report the maps of the 1dvar algorithm output from the TDP-v1. From left to right, we have the liquid water path and the total column water vapor in kilogram on square meter. These two variables are, as I told you already, included in the output file. The first one as a prior product, and the second one as a diagnostic variable. Then the other two variables are the surface wind speed over ocean in meter on seconds, and the surface temperature in Kelvin. These two variables, even if they are in output to the 1dvar algorithm, they are not included in the file, in the output file, mainly for size constraint. From the map, you can see how the liquid water path, so the MWI level 2 product, is not derived over open ocean, over sea ice, and over precipitation here. So this surface type pixel and this precipitation pixel are screened out before applying the algorithm itself during the so-called pre-processing phase. Okay, here just an example of an overall quality flag, which is included in the output file and provides to the users some useful information on the quality of the liquid water path. Essentially, it tells us if the product is nominal, degraded, or even missing, or eventually even not performed due to surface type or precipitation screening. Together with this flag, we have a lot of other flags that are included in the file, but I have no time to explain them to you in this presentation. Okay, now I move to talk about the level 2 ICI product that are included in the test data packet V2, sorry, V1. From left to right, we have the ice water path in kilogram on square meter. We have the mean ice mass height in kilometer, and we have the mean particle diameter in millimeter. All these products are included in the output file. So we can see also that they are derived over all the surface type pixel. This big hole that you see here over Africa tell us that the Monte Carlo algorithm does not run in obviously clear sky conditions, so that are accurately selected during the pre-processing phase. As I have done already before for the MWI level 2 product, I show you also a quality flag for the ICI level 2 product. This ice water path retrieval flag tells to the users if the product are nominal, are degraded or missing, or not even retrieved because of clear sky conditions. So essentially, again, we have a lot of other flags that are also other quality indicator that are included in the file, but I unfortunately have no time to explain them here. It is worth to mention here that at the beginning of 2023, the test data packet V2 will be made available to the users, will be published on our website, on the EUMETSAT website. It will contain 3 orbits and will be made of more realistic radiances with respect to those used for TDP-v1. TDP-v2 will implement also the graded conditions like gaps, non-nominal calibration counts, and so on. And also it will consider all the functionalities that have been not considered for TDP-v1 that I have listed in a previous slide. Okay, before talking about the last topic of my presentation, that is the data dissemination, I would like to show you this figure that resumes the main steps of the data flow, from the sensing of the raw data at satellite level. So then these data are acquired from our ground station, and then they are processed into our EUMETSAT mission control center at the EUMETSAT headquarters in Darmstadt, where the product are generated. I will not go into details of these slides, but I just wanted to show you the complex structure that is made of a lot of interfaces and a lot of different entities that is behind the generation of the data that the users will receive operationally. Okay, this is, I think, the most important table for the users, because it contains the format of the data that will be disseminated for a global and regional mission for the MWI and ICI level 1 and level 2 product. In addition to the native NetCDF format, we also provide the buffer format disseminated via EUMETcast. And for level 1B, we have also the WMO, so our buffer file will be disseminated via the WMO Global Telecommunication Service, GTS. But please consider that the buffer file disseminated via EUMETcast will be different from that distributed via GTS. Because the file disseminated via EUMETcast will be different from the buffer disseminated via GTS, because the GTS has a specific requirement in terms of file size. Essentially, the files should be of the order of few decades of a few megabytes, so around 50 megabytes. In my last slide, I show you the EUMETcast data dissemination services, which we can divide into push and pull services. With the push services, the users receives directly the near real-time data via satellite or terrestrial network using a EUMETcast station. With the pull services, it is the users that can visualize, customize, and eventually download our data directly online by prior registration to the EUMETSAT EO portal. Here in this blue box, I report some useful link that can be seen by the users. In the last column on the right, I show you also some additional services that can be useful for the users that wants to receive the current and past data from EUMETSAT and want also to learn more in details the content of this product, for example, using this product navigator that is available online. As a summary, we can say that the MWI and ICI level 1B and level 2 product have been defined, and the implementation of their operational processor is progressing. Product format have been defined using NetCDF4 as a native format, and they are fully described in the product format specification document. Global and regional product follow the same processing, and their format are identical. The first version of the test data is publicly available, and a new version of the test data will be released at the beginning of 2023 for both level 1B and level 2 product. EUMETSAT, as a last point, EUMETSAT will provide already to the user several services for data reception, downloading, customization, visualization, and exploration. So thanks a lot for your attention. I would like to ask you to Srerika if there are any questions or comments.
There are indeed questions, Francesco. I will just share my screen. Thanks for the presentation, for the very detailed description about the formats and everything. Very useful, I think, for the users when they actually get the data. So Francesco, just bear with me. I think they are coming up actually. It's just a time lag there. So I don't know how these questions are ordered, but anyway, just take the first question from Nigel there. Nigel has asked, please, could EUMETSAT mention the fact that the NWP SAP's MWI PP package will include tools to ingest and process MWI ICI level 1 data, including generation of a collocated product in buffer for use in NWP. A release is planned for early 2022, compatible with EUMETSAT's test data. Nigel, I think this is an information for the users. Yeah, if you want to respond, you can.
Okay, I was not aware of this, but yes.
Yes, thanks actually, Nigel, for pointing this out.
Good.
I think this would be very useful for the users. And yes, I can confirm, and this is very good that we can mention this in the webinar, actually. Thank you, Nigel.
Okay. There's another question. Which RT model was used to produce the TDP version 1 data?
So regarding this question, so we used the instrument data simulator that have been provided by the industry to ESA. Essentially, this instrument data simulator provides us the instrument source counts. Sorry, the instrument source packet as they will come in the real with the real data from the satellites. So we used these packets, and we have processed these packets directly with our in-house prototype. With our in-house prototype.
Next question.
We can say,
okay.
We can also add that yes, for we use as as input to the IDS in this respect. We use the test PAM TBs that use as a RTM, as a radio transfer model, the successive order of interaction 3D slumped radio transfer model.
So this was for the earlier question, yeah, which radiative transfer model?
Yeah, for the TTPV2, we are going to use a simulation using ARTS from Chalmers University and other universities.
Okay. And this is the next question. What kind of spectral response function is used to produce MWI TDP version 1? Are measured spectral response functions available for MWI and ICI?
The MWI and ICI spectral response function will be available, are not currently fully available. So there was not when we had to produce the data. So there was just the central frequency of the double sideband average that was used for this early test data. But in the end, when all these measurements will be completed, the spectral response function, we would like to provide it to the users.
Okay, Vinia. Thank you. Will there be any joint MWI ICI retrieval products in the level 2 output?
This was I think was already replied by Vinia in the previous questions, but indeed in the level 2 product there will be the live water path that is derived from MWI and the ice water path derived from ICI. At the moment is not foreseen any combination of MWI ICI level 2 product.
Thanks. There's another question. Could you confirm that the MWI level 1B granules will hold only 135 scans? It's 42 granules per orbit, scales down to 25 megabytes. If so, why not provide full lat-long information and TBs in addition to the radians?
Regarding the first question, this is the last baseline available. So from the program. So this will be at the moment, this is the last information available. So it's 135 scans per orbit. Regarding the full latitude and longitude information, but this will require a lot of more size in the file. And so this means also a larger capability of storage, or store this data. So this was an internal decision then.
Mm-hmm. So I tick that question.
Yes.
Okay, I think that's a date question, version 2 of TDP. The test data package V2, yeah?
Yes.
2022 or 2023?
It will be released in 2023. So both MWI and ICI. Yes, both MWI and ICI and both level 1B and level 2.
Together, yeah?
Yeah.
Okay. I think this question is now answered. This is from
together,
the last.
Together, I'm not sure, Sarika. It could be that the level 1B will be published before the level 2. Because of course, this is the chain of processing the data. So.
Okay, I think this was answered through your whole talk, actually. I think that's, if that is what we understood, yeah, what are the available data sources? I think that's fine. I think there is another question about this type points compression. When compared with the total size of the level 1B file, would it take so much space to include full resolution IFOV geolocation instead of type points for MW and ICI?
This including for the full orbit, it's around 500 megabyte more if we include the full resolution instead of the type points. So this is so essentially it's half of the size of the MWI already, because MWI is 1.1 gigabyte per orbit.
Okay, so that justifies use of type points.
50% more.
That's maybe the last question for you now. What kind of reconstruction method would you advise for calculating the full resolution IFOV geolocations from the given type points? For example, Lagrangian. This is a method that you said is explained in the PFS.
Yes,
you can also explain it here, please.
It's explained there, but it's essentially it's a simple linear interpolation. We apply a simple linear interpolation in the HF coordinates. So it's very simple algorithm, but it's fully detailed in the PFS.
So I think in the presentation you have given a link to the test data, and together with the test data we have the PFS also available. So
there is also the link directly to the PFS. Huh?
Yeah, yeah. In the presentation there's a link to the PFS also.
Yes, as well.
Okay. Thanks, Francesco. I think thank you for the good talk.
Thank you.
Useful talk, actually. And that also means we take a break now. We are a bit late, but I think it still take the 5 minutes break as we all probably need it. So we will be back by 15:33 CEST, which is, oh my God, 13:53 UTC. Thank you. We'll come back.
So welcome after the break. I'm going to share my presentation because after we now heard so much interesting details about the MWI and ICI instruments, I want to bring you a little bit back to nature. You can see here the full complexity of clouds, which we want to explore with these instruments. And I think we will get very exciting insights which haven't been gathered yet. So that's the content of my talk, and I will guide you a little bit through the motivation, the information content of the ICI signals, radiative transfer, retrieval, and some outlook. I start with a nice plot from Dave Duncan's paper. I actually saw him in the audience, and I think it's a nice overview about 4 satellite products and 2 reanalyses, which shows that while of course we know that in the subsiding branch of the Hadley cell there are hardly any ice clouds, otherwise there's quite some discrepancy between the different products. And that's why ice cloud information from ICI is so crucial. But let's look a little bit more into this by looking at the zonal mean values. And here you can see this, these different products, and we see, in fact, an order of magnitude differences between the different products. And you also notice that one difference is what is actually an ice cloud? What is the water belonging to cloud size, like a small particle, and what to the larger particles. And in fact, this is here divided by era 5, where like in models, you have a very clear boundary, what is counted as a cloud ice water path and snow water path, while of course nature is much more continuous, and there are also new approaches in modeling, which are not going into these bulk categories, but allowing for more complexity. So that is important because, as we see, we have to somehow constrain our knowledge. And that the different satellite products are so different is explained a little bit by this nice sketch, where you can see that in fact at different wavelengths, different vertical layers of the cloud are probed. So with visible and infrared techniques, in fact, only the upper part of the cloud is seen. There's also quite some work recently on MODIS techniques, assuming like different vertical structures. But nevertheless, these kind of techniques see just the light clouds in the upper parts. Especially LiDARs are very sensitive for the upper part, but very accurate there, while the active microwaves, they basically have the disadvantage of the poor spatial coverage. As you saw before, the data product is believed to be the most accurate, combining LiDARs and radar information, so going through the cloud, but still it's very poor coverage. Plus, if we go to the large particles, there's also uncertainty getting into the game due to the particle habits. And when the current passive microwaves below 200 gigahertz, they basically only see the precipitating eyes. Now, the new player, the submillimeter range, will get in, and here it fills the gap, and together with MWI provide information over the full extent of the clouds. And the main product is the ice mass and the mean ice particle size. So looking a little bit more into how this information is transferred from an electromagnetic measurement into a physical product, this sketch illustrates that the thermal radiation emitted by the surface and the atmosphere is scattered by ice and snow particles out of sight of the satellite instrument. And let me get my laser pointer. This, of course, this process depends on the wavelength. Still, if we look here as a function of the amount of ice particles, one can see that for the highest frequency, here in this case, the 875, there is already at this low amounts of ice water path quite a strong decrease. So we have a clear relation between ice water path and the depression in the brightness temperature. So this was like a major motivation also for getting this frequencies. We work with Stefan Bühler. And if we look how this submillimeter measurements fill the gap, I like this figure quite a lot, where we see what I said before, that in the infrared, really with small sized particles give a signal in terms of the brightness temperature, and that the radar, which is sensitive to the larger particles, the signal disappears towards this mid-range of the hundreds of micrometers diameter. And then if we look at the sensitivity for the ICI frequencies, we see the different parts of the size spectrum are probed, and that in this way, the full spectrum of sizes and also the vertical range by the different transmission will be probed. So in this respect, as you find also in our documents, ICI's primary objectives are to support climate monitoring, validating ice cloud models, and supporting the parameterization of ice clouds and weather and climate models. And so the ice water path, as demonstrated here before from Francesco and Vinia, is the primary product, and it can be already seen in this spectral plot that basically different frequencies, the depression relates to the ice water path. So now moving a bit further, because I would like to convince you that there will be quite some explorative science possible using these data. And one of them is the snowfall distribution. So of course, this is for numerical weather prediction, as you can clearly see. And I will give an example of a storm later, regions of strong snowfall. One thing I'm personally very interested is in looking also into the polar regions and seeing the change in precipitation. Other objectives are here the ability to initialize the models, and Alan here will later talk about assimilation. Another aspect which is also always discussed is, will we ever get a microwave or maybe at least a sub-millimeter on a geosensor? So how could this help in providing more information on precipitation? But I think there might be some surprises still ahead of us, because it's the first time that sub-millimeter wave observations for meteorological purposes will be made. So it will be a strong coverage, so we can see many effects. For me, it's kind of a reminder of the times of my PhD, where I used the 649 for ozone chemistry. So, but here, if we go to the meteorological exploitation, as I mentioned before, we get the radiance observations as detailed by Francesco, and then this direct radiance assimilation using fast radiative transfer models is a key application for numerical weather prediction. And here the RT-TOF model is of special interest. Also, we have heard that we have retrieval algorithms. So they are often developed from output by atmospheric models. And furthermore, like in data assimilation, this atmospheric model fields, the forward operator could convert this also to radiances. So looking at the whole chain here, I think it's a constant learning process also between the observations and the modeling, with the radiative transfer playing an enormous role in that. And therefore, I want to say a few words about radiative transfer modeling. And as you can see, or have heard before, it has been really fundamental to do pre-studies using radiative transfer modeling, and the ARTS model has played a huge role there. Furthermore, while ARTS is a very detailed model, allowing a lot of different testing and sensitivity, for data assimilation, we need something fast. Also, and there was even this question in the previous talk, it's important to generate the test data and then build the basis for retrieval development. And we ourselves at Cologne, we use the PAMTRA model for the interpretation, but as I said before, there are a few detailed radiative transfer models which can do the job. So, but basically they all have an input, we have the atmospheric state, the hydrometeors, and of course the boundary condition, like the emissivity constraints they use. And I want to focus a bit on the challenge which we are facing if we extend our research to the submillimeter range. One is the gaseous absorption, and the other is our single scattering properties of a hydrometeor. So in fact, the gas absorption is an aspect where different models show quite some discrepancies. And that's why this is also highlighted in the ICI science plan, which Vinya already introduced. And in fact, we have many more lines in the submillimeter region compared to the classical microwave range. And furthermore, there's much less characterization of the water vapor continuum. And therefore, we had a very nice workshop at EUMETSAT, which is reported on in this BAMS paper. And in that also, the need for validating gas absorption models has been phrased. And they are ground-based measurements, as they are, for example, performed from colleagues in astronomy, and also airborne measurements have been mentioned. And in fact, there are ongoing studies which make use, for example, on the ALMA observations from the Atacama, where we have ideal conditions to relate the measurements of the atmospheric state to measurements from the telescope operating through the spectrum in the submillimeter and even terahertz range. The other point as a challenge is the hydrometeors. And I already mentioned the importance of the numerical weather prediction or climate models and their cloud schemes. So here you see an example of a two-moment microphysics scheme, and each of these colored lines represents a process which has to be parameterized. And it's a two-moment scheme, so having mixing ratio and number concentration. And it classically shows you how complex the whole story is. And it gets even more complex if you look above, that the different ice particles can have very different sizes, while, for example, normally a very simple assumption on the type of a snowflake is done in such a microphysical model. So therefore, this, as I said before, this interplay between the modeling in cloud schemes and rate transfer is very important. So this is also something where a lot of interesting work is going on. And recently, several papers also looked at these aspects using measurements from the GMI, where like the 166 gigahertz window frequency, where both polarizations are available, can serve as a proxy. But still, we are going to extend to the sub-millimeter range, so up to 600 gigahertz, where we still will see quite some development, I'm pretty sure. So how can we check these kind of microphysical schemes? And this is an example from Wang, who used WRF model simulations, which was like one moment, so just the mixing water content of 5 hydrometeor species. And you can see that you have different species going on in this scene. And of course, you can employ different microphysical schemes. So in fact, you have different concentrations when on the hydrometeors, and one can simulate now, based on these volumes, the brightness temperatures, and check what is the influence on the results, and could we, in fact, with our measurements, which will come, see which kind of assumption work best. But here, not only the brightness temperatures will be of interest, but also information from the polarization measurements. So here you see an example again. Now you saw the brightness temperature depression several times with increasing frozen water path. And so note that this is the sum of all frozen species, the cloud ice, the graupel, and the snow. There is this depression. There's a little bit of color to be seen here, and this becomes more visible if we now look at the brightness temperature difference as a function of the frozen water path. And here the different colors separate, and they are an indication of the alignment of the particles. And in fact, if you now do in the diagram the polarization difference as a function of a brightness temperature, everything here at the GMI frequency of 166 gigahertz, one can see for the particle type of large plate aggregates, at least some of these curves agree rather well with the zonal mean observed by GMI. So this is a way to check with observation whether our assumptions on the particle type and their single scattering properties agree. And to illustrate that this matters, you can also see the same analysis using a different habit. Now, the polarization might include some more information, which we maybe not yet, but I'm sure later on make more use about. And here it will be very interesting because with ICI we go with dual polarization measurements to 240 and 660 gigahertz compared to what we had before. And this is similar as before, just different types of profiles are used here. And we see the relation with the snow water path. But what also needs to be considered is what happens if you have an absorbing layer like a supercooled liquid. And in this respect, it's good to see that this does not matter so much at the high frequencies, but more at the lower. So there's some differential information which can be exploited. And last but not least, here's a nice example where you see a storm in Argentina. And the black and the red line, they give the coldest parts of the cloud, and the colors, the polarization difference. And now we can see that in fact one sees the difference at the higher frequencies between the stratiform part where the particles are lined and the convective regions where one has a smaller signal. Now, concluding is that we can certainly learn something on cloud microphysics from such data, which we might maybe not see yet. I'm seeing that I'm running out of time, so I will very briefly present you this operational retrieval. There are a lot of efforts have been put in, and there's a paper by Patrick Eriksson where you can check in more detail the data flow and the underlying data sets. And just maybe to take a number for accuracy in that is that here these colored dashed lines span the 2 sigma difference, and so because this is a Monte Carlo integration retrieval, we can say that with 90% confidence our knowledge is best with 50% of the integrated water path, ice path. Also, information about the mean mass height and the mean mass diameter can be inferred. There are also other approaches, and maybe what one can see from this, if ICI and MWI are combined, the accuracy is getting better, and we can reach 20% accuracy around roughly 1 kilogram per square meter. So just before coming to the end, I want to present you some airborne measurements. And this is taken here from the Polar 5 aircraft, where radar is in the belly pod and a cold air outbreak was probed. And you can see in the measurements from the radar below nicely this convective cells and brightness temperature measurements at 243 and 340, which also show you the different penetration depth. So 340 is much less transmissive. Now we take modeling results from the ICON model, and you can see that neither the radar nor the brightness temperatures match very well. When modifying the scheme in terms of the nucleation particles, one can see that a much better agreement can be reached. So again, highlighting the interplay between modeling of microphysics and radiation. Vinja and Francesco also highlighted the ISMA instrument, which has also been flown on the farm from the UK. And also there, I tried to give you a lot of references. You can find studies on relative transfer modeling. So I want to conclude with summing up some important points, what I hope you took away from my short talk. That ICI is a very interesting, relatively low-cost mission, which will complete the existing satellite measurements. And there will be quite a lot of application from climate monitoring to weather forecast. And Ellen will talk more about the operational aspect, while I hope I could convince you that we can learn quite a bit on process understanding and how, if we come back to my first slide of the clouds, how we can enhance the process model. So we have still some time to go, but I'm looking back already impressed how much better the modeling of the radiative transfer and the understanding, for example, of the single scattering calculation has become, and also like with the new observations going on from aircrafts, I'm sure we will get prepared very well. Also the cooperation with astronomy on the gas absorption model. There are more retrieval developments going on, and especially the polarization features will provide new information. So thanks a lot for your attention.
Thanks, Susanne. It took only 3 minutes extra, so don't worry.
Okay. Yeah, my students don't want to wait 3 more minutes.
That's okay. I just, before I think maybe people need some more time to post their questions. I will just give an information that we have a poll open. Actually, there's the link in the chat to give us some feedback on today's sessions. And then we take the next question. So hopefully you can put in some more questions, okay? Susan, I will bring up the question now.
So shall I answer the question? I see.
Yeah, there was one. Let me just bring that up first, because I think there was a question on the
emissivity.
Was it on the yeah. Okay, this I can bring up. I thought there was also a question on the information, you know, from Vinia's talk, there was a question on the research, the research products, but that you cover in the, do you remember that one that you wanted to answer?
No, my comment was more that I provide some general,
which is
background information on
which is what you did now, yeah?
Yeah.
Yeah. Okay, then I bring up the question. I don't know why I can't see the, oh no, this is because it's a poll. That was the poll question. Okay, that's a question on the emissivity. What is the impact of surface emissivity at different frequencies that has to be taken care of during the retrieval?
Yeah, I'm actually very happy about this question, because a student of mine who is doing his master thesis on that is also attending. And we are looking for the Arctic measurements on this aspect, because the higher submillimeter frequencies have much higher optical depth than the others. Normally, surface emissivity does not play so much of a role because the surface contribution is low, but the less water vapor, the less clouds are in the atmosphere, there can be a contribution from the surface. And in fact, the emissivity models are often just an extrapolation. So this is something also Kathleen Pujong is looking at. And it can also help if we get some information from the surface, because the geolocation is otherwise pretty difficult, and the high altitude lakes have been identified as an interesting area where one could see the difference between the emissivity of the water and the land, and also help in geolocation.
Okay, good, Susan, thank you. Oh, there's a request. Could you please dwell 1 second on the slide showing neural network retrieval from ICI?
Shall I share?
I will stop sharing and you bring up your slide, okay?
It always takes some time.
No, don't worry.
Okay. Is it okay if I leave it in this mode?
Yeah, I think for explanation, this is, I guess, enough.
So here's also the reference to the paper. And in fact, there is something I didn't say here, which I think is very crucial, which is the reason for the really good performance of this algorithm. And this is that before applying the neural network to get the frozen water path, first there's a classification of the scene in terms of the hydrometeors present. And that certainly helps to already refine the knowledge on the state of the atmosphere and apply an algorithm which also works under these conditions and is not as broad as if all parts of the atmosphere would be considered. So I don't really know what further information I should give on that. The basic thing is that you can see the relative retrieval error as a function of the frozen water path, and this is the same result as from the paper from Patrick, that if it's very low, of course the uncertainty is much higher, and then it's reducing. I would say this is here basically in the 40% range, the ice cloud mode, and when we go more to the thicker clouds, and when we already see here at 1.5 kilogram per square meter that it gets noisy because there are not so many events also in this database.
Okay. Thanks, Susan. I think you also have a link to the paper, so maybe they can refer to. I mean, I also liked that you gave references to all the papers that you described, so we can go back and check. Yeah. Thanks, Susan. I think we move to the last speaker. I would have considered to give a break, but I think we should finish in time, otherwise it's not fair. So we give the floor to Alan. Go ahead, Alan.
Oh, yes, thank you. Yeah, thanks to EUMETSAT for the chance to give something of a user perspective on the use of MW and ICI at weather centres, and in particular at ECMWF. So, you know, what are the benefits of these instruments for weather forecasting, and how are we preparing for it, and how is the community preparing for using the data, and where are the difficult areas? So let's get started. So first of all, just that motivation for using MWI and ICI for numerical weather prediction for weather forecasting. So we can start that discussion by looking at the geophysical sensitivities of the radiances, and you can see this really just by looking at maps of radiances at 19 gigahertz, horizontally polarized, representative of the lower frequency window channels, and 183 plus or minus 7. Although it doesn't have so much sensitivity to ice cloud as some of the new ICI frequencies, it's still fairly representative of the kind of things you might see in some of the ICI channels in the broader details. So together those two channels cover a lot of the information content. And then I'll bring it up on screen, sort of pointing to the areas where that information is found. And the colors indicate kind of current state of the art for using that information in weather forecasting and how we do it. So, for example, land temperature, soil moisture and vegetation from these kind of microwave images is not used at the moment in weather forecasting, but we're very keen to start using it. Same with the snow information, higher frequencies from the polar regions. You can still see the surface, and at low frequencies, you can almost always see the surface and are sensitive to that snow. The same with the sea ice, it's very clear to see in the high frequency window channels. Sorry, just going back, so that blue color means that we do use the information from some microwave images in weather forecasting, but it comes in an indirect form into our system through external retrievals. What we do use directly through assimilating radiances in all sky conditions is the sensitivity to the water vapor, the cloud and the rain, and that elevates the brightness temperatures over the ocean in that example. The surface emission is also important, and the surface roughness is sensitive to wind, so that's something that we also see in the brightness temperatures and infer with our radiance assimilation. Not so much the ocean temperature side of that signal, but which is also present. Frozen hydrometeors we're directly sensitive to, and we're directly assimilating in the assimilation systems at the moment. And those higher frequency water vapor sounding channels see very clear signals of variations in water vapor in the mid and the upper troposphere. And that brings a lot of information on wind into our assimilation systems. And what else? Just to point out that these blues up polar latitudes in the 183 gigahertz and even into the ICI frequencies are coming from scattering from the surface from snow and sea ice. And that's dependent on the grain size, the humidity of the ice, the surface reflection. So there's some really interesting physics there, which is not yet assimilated, but we would be interested in using in the future. So we'll come back to that in the talk. So just go through 4 motivation slides for what we get out of microwave data at the moment. Is really that it's one of the dominant sources of information in weather forecasting, especially at ECMWF, where this pie chart shows the impact of the different observing systems that we have on the 24-hour forecast quality. And the microwave water vapor chunk is around 18 to 20%, so it's quite a large part of the impact, and that comes from 14 different microwave sensors. And this, what we call water vapor, includes window channels, microwave images, and humidity sounding channels. So that's exactly the kind of data we'll be getting from MWI and ICI. And as hinted at in the last slide, that impact, a lot of it seems to come through a kind of tracing of features of cloud, of water vapor. From that tracing, we can infer not just the winds, but the rest of the synoptic state of the atmosphere, and do better weather forecasts as a result. Something that we're trying to develop is to use the obvious sensitivity of these instruments to really important details, microphysical details of cloud and precipitation, to tell us something about our forecast models and whether we can improve the parameterizations within that. And Suzanne has already actually shown a very nice example of that in the last talk. This is another example using a cost function between ECMWF simulated and SSMIS observed radiances, and low is good, high is bad. And on the x-axis is a series of different particle types from the ARTS database that could be used to represent the convective snow particles, going from light fluffy particles, the column aggregate, through to heavily rime particles like the Graupel. And this cost function at least found some particles in the middle, which we're now going to use as our standard particles in RT12. And the colors just show that that solution was quite insensitive actually to the convective snow mixing ratio. So the point, the more broader point, is that many important microphysical parameters in our forecast models and in our observation operators that are not well constrained at the moment, and this data will certainly help us do that. Number 3 is coming back to that more surface sensitive aspect of microwave data, even including ICI data. And a big part of ECMWF strategy at the moment is to improve our Earth system analysis. That means ocean, sea ice, and land surface variables, for example. And this is just an example that you can quite easily get sea ice fractions out of microwave data. I mean, that's one of the main sources of sea ice data generally already. And we would hope in the future to use direct radiance assimilation to infer that sea ice fraction from data like MWI and even ICI perhaps. The final motivation is more something that NWP can potentially provide to the community, which is the weather forecasting system as a reference for calibration and monitoring, not an absolute reference, but a relative reference. And this is just an example from SSMIS, which is over a 4-year period. This is day on the x-axis, and then following the sensor through the orbit. So this is the orbital angle on the y-axis. You can see the mean observation minus background departure in Kelvin, and there's some quite interesting features here to do with the calibration issues that SSMIS has to do with the solar intrusions and solar heating generally. And one example here is this. This is the satellite coming round the South Pole. It's in darkness, and then as you come through into the sunlight, there's some kind of heating or solar intrusion that occurs, changes the calibration of the instrument by a couple of Kelvin, and then it settles down again thereafter. And those relative changes in calibration are really the key thing that weather forecasting can identify through the orbit through time. So moving on, Suzanne has already touched quite a lot on this, but the key to using MWI and particularly ICI is to have a fast radiative transfer model available for weather forecasting and data assimilation that's capable of doing particularly sub-millimeter radiative transfer in all sky conditions. And in Europe, that's generally provided by RTTOV. So what's RTTOV? It's a operationally targeted fast radiative transfer model. I've just got a screenshot of the web page here and a link to that for those who aren't already aware. And a lot of the European effort towards improving radiative transfer at the sub-millimeter is feeding into RTTOV, and I'll just show a few examples of how RTTOV is being prepared for ICI in particular. The first area, which again Suzanne has touched on already, is the gas spectroscopy, the different water vapor lines, the continuum, and other species lines like oxygen and ozone. And I won't go into details, but there are some references here on a lot of the development work that's being done in EUMETSAT funded studies, work at the Met Office, and within the NWPSAF consortium, which develops RTTOV to improve the gas spectroscopy and our knowledge of that and our knowledge of the uncertainties in advance of the mission. Another thing that I just wanted to highlight was the refractive index, or the permittivity model, is also something to think about, and that we did have to think about for RTTOV looking forward to ICI. We've got various different available refractive index models, permittivity models here in different lines, and this is the frequency above 300 gigahertz is where ICI will be, and there's quite a big spread in the different currently available models. So we think we've made a reasonable choice, which is the Rosenkrantz model for those higher frequencies, and that will impact the quality of our simulation of cloud and rain. So that'll be something to look at when ICI is launched to see if that's really the right choice. Moving on, we need to increasingly think about the size and shape of the particles that we're representing in our radiative transfer models, and this relies particularly now on the ARTS database, which was created with ICI in mind. This is an example of some brightness temperature simulations from using the ARTS database particles, but also assuming a particular particle size distribution. And these are the brightness temperatures as a function of frequency. So you can see that with that range of different ice particle shapes, we can simulate a very different range of brightness temperature signatures as a function of frequency. And so that will help us simulate the right radiative transfer for the situation, and indeed also identify the kind of particle shapes that we might be seeing in the radiances. On top of that, we've been preparing more flexibility and more availability of different particle size distribution options in RTTOV, and that's increasingly important at ICI frequencies because, for example, cloud ice, some of the millimeter sized particles, we're going to need to describe the number concentrations of those particles very accurately in order to do a good job of representing the radiances. So those are all there in the RTTOV package with defaults that we think will be reasonably good for ICI, but of course that will be revised in light of the actual operational radiances being available. Moving on, another aspect that Suzanne has touched on was the polarization in these radiances. This is an example based on the Brath et al. Particles. This is the state-of-the-art representation in the community at the moment of particle orientation, is to assume that the azimuth orientation of the particle is random, but the tilt angle of those particles is fixed. And these are simulations of the relative difference in particle extinction between vertical and horizontal polarizations at different tilt angles. And for preferentially horizontal particles, which we think are quite prevalent in the atmosphere, as you've seen in Suzanne's talk as well, then there's a much stronger extinction in the H polarized radiation than the V. This is relative to the ratio. The incident angle is this. This is the zenith angle of MWI and ICI. So there's going to be relatively strong polarization that we'll see. So how do we represent that in a fast model? So there's already now in RT12 version 13 a fast parameterization of the particle orientation effects and their influence on the polarization. So this is the polarization arch in red from the observations as a function of the 166 gigahertz observed brightness temperature, and polarization goes up to at least 10 Kelvin in the middle of that range and then falls. And the earlier version of RT12, which is in green here, didn't have any representation of particle orientation or polarization. And the version 13 has this simple perturbation of the extinction of the particle or the bulk extinction as a function of a ratio rho, and we just adjusted the rho ratio to fit the observations with 1.4 as the best number for the moment. Again, maybe frequency dependent, might need to be revised in light of ICI as well. What else? So the surface emissivity is going to be really important. As I showed you right at the beginning of this talk, at 183 gigahertz, you can still definitely see the surface at polar latitudes, and you can see sea ice, you can see snow. And that will carry on into the ICI frequencies as well. Now, there has already been some preparation for sea surface emissivity for the higher frequencies in this publication here that I've cited, but also there's an ongoing work on a new model called Palmio, which will also cover that range, and hopefully that will feed into RT12 in the next year or two as well. So hopefully that's the sea surface emissivity side is covered. Possibly the more difficult thing is dealing with sea ice, snow, and land surfaces, and our traditional techniques of using atlases may not necessarily work if we don't always see the surface, but we still have some sensitivity to it. So I'll show you what this next bullet point means in a moment, really, but essentially we'd potentially think about retrieving snow and ice properties using the lower frequencies and then somehow physically extrapolating those frequencies to represent the surface radiative transfer at the ICI frequencies. Which brings to this point of thinking about MWI and ICI really as one instrument from a sort of scientific and weather forecasting point of view, because we need all those frequencies to constrain the unknown microphysical aspects of the clouds, but also the unknown microstructural aspects of the surface, the snowpack, the sea ice. So what do I mean by that? These are retrieved surface emissivities from SSMIS again. These are from the IFS ECMWF data assimilation system again. And I'm just looking at one location here over the sea ice. This is multi-year ice as it's known. The emissivity at this point is shown as a function of frequency in this green line. The emissivity goes very low. That's down to volume scattering in the snowpack. And the big question for ICI is, how do we extrapolate to those frequencies for some of these really interesting surface types which have really strong variations of emissivity with frequency? And as I mentioned in the last slide, one possible way of doing that is to use observations at the lower frequencies, say from our MWI, to constrain those properties and then to physically extrapolate. So make physical assumptions and physical radiative transfer modeling of the snowpack or the sea ice to represent the emissivity at the higher frequencies. And in opposition, also on top of that, using those higher frequencies to constrain some of the physical modeling, because some physical models that work at a lower frequency may well not be appropriate for the very high frequencies. So that should be an interesting scientific development for the next few years. Also, just quickly, again, thinking about MWI and ICI together, this is the brightness temperatures simulated from a theoretical cloud over either a cold reflective surface or a warm surface, and clouds composed of 5 different standard particles that we have in RT12. And without going into the details, the thing is, across the frequencies of MWI and ICI, we see a huge variation in brightness temperatures, and we need those higher frequencies to distinguish between the different types of snow and ice particles. The lower frequencies also constrain the snow and ice particles quite a lot, and they also constrain the liquid particles. So you can think about all of these different particle types, particle shapes, different phases of particles as having spectral signatures across this whole range. And if we're observing that whole range, then we have a much better constraint on what those particle microphysical properties are. I've sort of highlighted composition and mass and shape. So again, that's a reason to look at the two sensors together. So new scientific possibilities. So these are the kind of scientific studies and interesting questions that we might be looking at when we start to look at how to use the data at ECMWF and in other sensors. Just a variety of different things to think about, not just the cloud microphysics, but we've got new temperature channels, hopefully very well calibrated on a conical scanner. That might be a first, and they might themselves bring some interesting new information to weather forecasting. Also, we've got a plethora of humidity sounding channels. So that's the thinking about ICI, not as a ice cloud imager, but just as a humidity sounder. It might bring new capabilities, and whether we can make use of that data is an interesting question, but probably we can, and we do get a lot of impact from humidity sounding channels on our weather forecasts. The first operational sub-millimeter mission bullet, it goes back to particularly what Suzanne has been talking about with the constraint on the smaller ice particles. So I won't cover that in detail, and also the combination of this very broad range of frequencies and a very broad range of sensitivities to different particle sizes, both in the atmosphere and in the surface, could be really powerful. One final discussion on observation processing, borrowing Vinya's slide here, showing you that the ICI footprints are not exactly co-located, and so we will have to, this is probably the main kind of technical scientific question for using the data at a weather center is what to do with these footprints that are not co-located when we want all the data co-located at one location. The solution to that is most likely to be superobbing. That's illustrated here with a black box is a fixed size on the ground, and we pick all of the fields of view that fall into that box and average them together. That's what we call superobbing at ECMWF, at least. And if you have fields of view that are larger, you just take the ones that fall into the box. And the point of this is to co-locate the channels and to standardize the field of view. And although it looks crude, it does a surprisingly good job if you do the maths on the fields of view and adding them together. And there are a range of different reasons that we do that, which are just beyond the co-location issue, but also in terms of using the data scientifically for weather forecasting. There are a lot of good reasons to do that superobbing as well. So probably we might as well just superob MWI and ICI together into one kind of super sensor to assimilate it, for the reasons I was explaining before, having that wide frequency constraint. And we have an ECMWF in-house tool, but as Nigel already pointed out, MWI PP, which is a new tool coming from MWPSAF, will also do that job and may well be what we choose to use in the future. So given that I'm also a little bit out of time, I'm just going to leave the summary up on the screen, just describing what I've already spoken about, and also the timeline, possible timeline of how we use that data and prepare for it at ECMWF. So thanks for listening.
Thanks, Alan. Great talk on an NWP perspective for MW and ICI. I will just seek the questions. Also, in the meantime, like I said before, please participate in the polls. Then you can give us some feedback on today's sessions. I will share the screen for the questions. Alan, I am stopping your screen sharing.
Sure.
Yeah. Mm-hmm. I see two questions there. So how do you compare the speed of calculation for the RTTOF scattering calculation with clear sky RTTOF?
I mean, I don't have don't have a good answer on that. I mean, yes, RT12SCAT is slower because it does essentially a two-stream like scattering calculation, which involves kind of matrix algebra and that kind of thing. It's significantly slower than RT12, but it's still extremely fast. There have been papers published a long time ago showing the speed, but I mean, it's slower than Clear Sky RT12, but still very fast and still very feasible to use in not just MWP, but most operational contexts.
And if you for spherical particles, and you might have comparisons done for spherical versus other shaped particles, etc. Or RT12SCAT can simulate for non-spherical particles as well, right?
So RT12SCAT uses these takes as input the scattering databases like the database I touched on.
Okay.
Indeed, without using non-spherical particles, we can't we can't reproduce the observations at any frequency without using non-spherical representations of ice particles.
There is another question on which scattering algorithm is used in ARTS versus RT12SCAT. Any comparison probably done between them for reference?
Yeah, a nice question. Actually maps on something I didn't have time to include in the presentation, but at Chalmers, led by Vasilios Barlakas, there's been a comparison between ARTS and RT12SCAT, and particularly focusing on the solver. So in RT12SCAT, the solver is the Delta Eddington, which I just described as a kind of two-stream solver. So that really simplifies the representation of the radiation as just being an isotropic up and an isotropic down. That's the two-stream. The Delta Eddington is slightly different, but it's not possible to explain now. Whereas ARTS is it has various different solvers available, but the reference is a discrete ordinates radiation transfer solver with in this case, in this study, I think 32 streams represented. So essentially it represents the scattering phase function, which can be very complicated, and the different radiation transfer angles in the atmosphere with a resolution of 32 essentially in angular space. And actually the conclusion of that study is that RT12SCAT will be okay for ICI. And there are actually a lot of historical studies also comparing Delta Eddington to higher order radiation transfer scattering solvers that also show similar conclusions, but for the lower frequencies in general.
Maybe I can suggest something. When you can maybe update your presentation, put up a slide with reference to that study if it is published, and then when we send out the presentations, then everyone can get hold of it. Is it possible? Yeah, no, definitely. I should be able to easily get a slide from Vasilios and add it to the presentation. That would actually be really good. Okay, that's great, Ellen. Thank you. I think with that, let me just check the chat message. No, that's something from all of us. So with that, I think we are in time to stop. It's 4:30. Thanks all the speakers. Maybe you can all, if your bandwidth supports, we can maybe switch on our videos and say goodbye. Thank you to all the speakers from yesterday and today. Thanks to Jörg Ackermann, to Imke Krisak, to Sabatino Di Michel, Vinia Mattioli, Francisco De Angelis, Susanna Crevel, and Alan Gear. But also we had some other supporters as well, like Christopher Akadia and Robin Eklund. So thanks everyone, but I have to give special thanks to Vesa Nitiswara yesterday and Madalena Unguru today, because they came in to support us at the very last minute, because we had some crisis period, and I thank both of them very much. And just a reminder for the survey, this will help us to perform better in our next webinar. Thank you very much, everyone. Bye-bye.
Thank you. Bye-bye to everybody.
Bye-bye.
Bye-bye.